And we'll be good to go. Alrighty. So welcome everybody to another NLP plus CSS tutorial. I'm super happy to have you all here. And yeah, this week is kind of a special one because we actually have one of the co-organizers, Katherine Keith, who's going to present a tutorial. If you're not familiar, Katie is a postdoctoral fellow at the Allen Institute for AI, and she's an incoming assistant professor at Williams College this fall. And she does lots of great work in causal inference as well as other domains. And this week, she's going to be presenting a tutorial about aggregated classification pipelines and how to handle probability sort of in different steps of an NLP analysis. So welcome, Katie, and why don't you take it away?
Thanks, Ian. Excited to have you all today. So yeah, today we're going to be talking about this aggregated classification pipeline. So I'm sure hopefully everybody in the audience has trained a text classifier. So we take some training text, we take some training labels, we train a text classifier, and then at inference time, you're going to take new text and infer some labels, right? And this has been a big workhorse of NLP plus computational social science because no longer do we only have to do manual analysis. But there's really two paradigms that I like to see with using text classification. The first is what we think about in sort of like conventional or traditional NLP is that we might have a pretty simple data set, like 20 news groups, where the label is just the type of text. But in the social sciences, we might have richer social constructs, such as moral outrage labeled on tweets, which is going to be our running example throughout this tutorial. And the difference between these two is often in conventional NLP, we have this assumption that there's one true label on the text. But we know that in the social sciences, right, humans can interpret texts in really different ways, and there might be some natural disagreement on the labels themselves. So an example here of a potentially ambiguous tweet is someone tweeting at a senator that they should clean up the garbage. Wait, that would take some effort, right? There's some sarcasm here and some ambiguity of whether this is classified as moral outrages or not. And so what we're going to talk about throughout this tutorial is how do we use things like this natural disagreement and the probabilistic uncertainty there and propagate it downstream. So if you take away one thing from this tutorial, I want you to take away that if your assumptions as a social scientist don't match those of conventional NLP, you don't have to give up. You don't have to stop right there. You can actually modify the code and modify your entire pipeline, which is some of what we're going to be talking about today. So we're going to use this running example from Science Advances 2021 about how social learning amplifies moral outrage expression in online social networks. And this is an overview of the pipeline. I chose this paper because I really think that social science expertise matters. I'm a computer scientist here. I'm trained as a computer scientist, but I really want to center and privilege sort of this social science theory and expertise. And this group of authors has done a lot of great work in psychology. They have a really thorough data and annotation process and research design. And my subsequent comments on this data pipeline should be seen as opportunities for future research and not necessarily a critique of this particular study. So we're going to go into detail of what this real world social science pipeline looks like in this aggregated classification sense. So they start with this research question, which is a causal research question. What is the effect of social feedback, their causal treatment, on expressions of moral outrage, which is their outcome? And if I draw the causal diagram, it looks kind of like this. This X social feedback takes the form of, for one user on the previous day, the total likes and shares on Twitter. The outcome is Y, moral outrage, which they operationalize as, for one user one day, the aggregate classifier's predictions across all a user's tweets. And they have many confounds here, which they adjust for. I'm not going to go into detail there. But this is repeated across all individuals at all time steps. And this is really one of the goals of one of the studies in this paper. Okay, so moral outrage we talked about is this rich social construct. So how do we actually measure it? How do we get an estimate of moral outrage? Like most classification pipelines, the first piece is annotation. So they take around 26,000 tweets. For each tweet, they have 10 annotators, and each annotator gives a yes or no label, a binary label. Is this moral outrage? And they decide then how do they take these 10 annotations and adjudicate to give one label for a tweet. And so oftentimes, and what is done in the paper is that you'll take a hard label by like a majority vote or by some sort of thresholding. And what we're going to do in this tutorial is change that assumption to have a soft label and take the mean across all annotations. And we'll go into a lot more detail here and give some examples, but we're basically softening this this hard decision point to make it more probabilistic throughout. So once we have this trained classifier that comes from the annotators, at inference time, the authors take around 4,000 users who are tweeting about Brett Kavanaugh's Supreme Court confirmation hearing. And for each user, they take one user's tweets for the entire day. For one of those tweets, they take their trained classifier and use it to predict a binary label, yes or no, is this moral outrage? And then they need to aggregate at the user day level. So again, we have this aggregation step. And what a lot of people will do is just take the hard predictions, these binary labels 0, 1, and just take the mean across them all. We're again going to soften that assumption and take the mean across probabilistic predictions here. So these are just a couple really simple ways that we're going to introduce this softening uncertainty and probabilistic assumptions, and then we're going to scatter some other points throughout too. So here's the whole overall pipeline. Although we're going to focus on this specific example, it's really a general framework that you can use if you have this, this aggregation, this aggregated classification pipelines. So my high-level goals for this tutorial, the first is to hope that you take away an understanding of a real-world social science research study, like we just talked about. The second is that we're going to make and soften these probabilistic aspects of this pipeline. And then finally, we're going to take some off-the-shelf code bases like Hugging Face and scikit-learn, and we're going to make some slight modifications for the code. So, you know, this is pitched as a 201 tutorial series. The 101 version would be to use the off-the-shelf tools, and in 201 we want you to start modifying them yourself so that you can have code and NLP methods that really fit your needs as a social scientist. Specifically, for annotation, we're going to shift from this hard label, which is majority vote, to this soft label. At classification time, we're going to take the hard labels and just train a standard hard classifier. But then we're also going to soften it. So we're going to take the soft labels and train with cross entropy loss on the soft labels and evaluate calibration error, which we'll talk about later. When we aggregate these predictions at inference time, we're going to shift from the hard predictions, taking the mean across those, to the soft predictions. So let's go ahead and move on to the code. But before I do that, does anybody have any questions about the general introduction and motivation here? Okay, for the sake of time, we'll just move to the code then. Can everyone see my my code here? Yes. Okay, so we just went through the slides of the background and the motivation.
Quick thing, would you mind sharing the code in the chat?
It's at the very beginning of the chat.
Oh, let me do that. I'll copy paste it.
Awesome. So, okay, we have some code set up here where we're just pip installing and importing packages. We load a small subset of the annotated data from this Brady et al. It kind of looks like this, where we have tweets, and then they had 5 conservative annotators and 5 liberal annotators annotate each tweet. So they did a really good job here of trying to make sure they're getting a balanced demographic panel for their annotations. And there's a couple assumptions we're going to use here. The first is that Annotators are not spammers. These are highly trained annotators that have been recruited over several rounds. Annotators' own judgments are calibrated. So 0 or 1 means the same thing to everyone. This is something you should definitely check in your own classification pipeline. And our final assumption is that disagreement is an inherently useful signal. And I've pointed to some other 301 extensions beyond this 201 tutorial that have dealt with things like adversarial annotators or correcting for annotator bias. I encourage you to look at that after this tutorial. So we're going to take these two adjudication approaches. Adjudication meaning we want one label for one tweet. We're going to take the majority vote, or we're going to take the soft label. So we're going to take the average across all annotators. And so you can see that for this first example, both the soft and hard label disagree, but there's other examples like the soft label is 0.4, this gets collapsed into a hard label of 0, or there's a soft label of 0.5, this gets collapsed into a hard label of 1. So here, you can already see what I'm hinting at is that the hard label is really throwing away a lot of information we have, which is if this disagreement is a useful signal, this soft label is going to be helpful here. So the means across all data instances are kind of close, but the soft label is slightly lower because of this aggregation rule. So like any pipeline, I think what makes text different from other data is we can manually inspect items throughout our pipeline. So here we're going to look at these items with this soft label that are quite ambiguous. So the ones that have the soft label of 0.5, if you run this cell, you can print them, but I pulled some out ourselves. So this was the one we used in the slides. So add a senator, you could be setting up the cleanup of all the garbage along Route 91 instead. Wait, that would take some effort. So, reading this, it kind of makes sense that half the annotators gave this a 1, half of them gave it a 0 because it's sarcasm and pretty difficult to interpret. All right, here's another one that's tweeting at New York Times, and I think a journalist, typical liberal thinking, #liberalism is a disease, right? So if we go back to this definition of moral outrage that the authors have provided, that it's feelings in response to perceived violation of their personal morals, there's emotions such as anger, disgust, and there's specific reactions, including blaming people, right? This is a really robust definition from these psychologists. This second example, it seems to express contempt, maybe with the hashtag, but it's really difficult to say, does this exactly map onto moral outrage here? So once again, I think the soft label of 0.5, that's pretty ambiguous, kind of gives us information about the ambiguity of this tweet here. Okay, so we've gone through this first step of annotation and adjudication. I'm going to pause again. Any questions in the chat so far? Okay, great. So now we're going to move on to training classifiers and evaluating performance. So like I mentioned, we're going to take two different approaches to training. The first is a hard prediction. So we're going to take this BERT tweet paper, which I'll talk about a little bit more as our encoder, and we're going to use negative log likelihood loss and the hard labels. For soft prediction, we're going to use the same BERT tweet encoder, but we're going to use a soft loss. So this is cross entropy plus soft labels. So just a quick review on loss functions. I'm sure you've seen this before, but just to set the stage. When we're training a classifier, our goal is to minimize the loss function, right? So when we're doing binary classification, both negative log likelihood and cross entropy loss take the same form, which is negative sum across all the examples of y sub I, which is our label from the annotators, log p sub I, p is the predicted labels, and then the reverse so that we get both binary settings, right? Y equals 1, y equals 0. So ideally, we want to take our soft annotation labels, right? If we believe our assumption that this has inherently, the disagreement is an inherently useful signal, we want to take those soft labels and put those in as the ground truth against which we're going to evaluate our predictions. And so there's some references here on people that have done a lot of experiments for thinking about the soft loss versus the hard loss. So we're going to see that we're going to have to modify the code because most standard libraries necessitate that y be integers, not real values. So we're going to have to modify these. So to give some intuition here, just a little cheat sheet about losses in PyTorch, which we're going to use. There's both binary class and multi-class. There's these different implementations in that are you applying sort of a sigmoid function or is the loss function itself. So here you might need to play around with these with your own setup, but we're just going to use this binary cross entropy loss where we need to apply the softmax here. So we're going to create some toy data, and what those look like is we have these hard labels and soft labels and two toy model predicted probabilities for the positive class. So you can see these predicted probabilities look pretty much the same, except for this second example, model 2 is predicting 0.9, whereas model 1 is predicting 0.6. So it's closer to this soft label of 0.1 for model 2. And similarly, in these last two examples, where the soft labels are 0.5 and 0.75 respectively, model 2 is predicting closer to that. So the takeaway here is that model 1 and model 2 would have the same hard predictions, but their soft predictions, model 2 should be better. We're setting it up as a toy example to understand this loss. So when we run this through the binary cross entropy loss, we see when we use the hard gold labels as opposed to the soft gold labels from the annotators. If you look at model 1 versus model 1, the soft label loss is lower, so lower is better here. And consistently across both of these gold labels, types of gold labels, model 2 is doing better, right? Which we should expect. So we're going to use this soft loss in the hopes that we can use our soft labels from the annotation and get more from those assumptions themselves. Okay, so we're going to use this BERT tweet pipeline. I've linked to the paper here. This pre-trains a Roberta training procedure on a very large corpus of English tweets. I'm not going to compare to a bag of words baseline just for the sake of time, but if this is your own pipeline, you probably should do that. We're going to use this BERT tweet model because pre-training has really taken off in NLP and will hopefully give us somewhat decent results. So we load the tokenizer. This is all from Hugging Face. So the authors have uploaded their BERT tweet model to Hugging Face and we can use their tokenizer. This does tweet normalization for us. I would encourage you to look at our previous tutorial that had pre-processing social media text. If you want to modify this yourself for your own pipeline, that's something you should definitely dig into. But for now, we're just going to use this sort of off-the-shelf tokenizer with this BERT tweet. So we create these dataset functions, and we are going to do a train validation split. So here I've taken a very small subset of Brady et al.'s large collection of annotated tweets. They have like 16,000. We're only going to use 340 just to make it quick and also give us some examples. I would encourage you to have much larger data sets in your own work, but I just wanted to show you that we can do it with a pretty small data set. So we're going to use 20% for our held out validation set that we'll use to evaluate, which leaves us with 272 training examples and 68 validation examples. So what we're doing here is just gathering the text, splitting them up into train and validation. We encode with this BERT tweet tokenizer, and then we gather the labels. We're doing both the hard and soft labels. And finally, we can look at sort of the mean labels across these splits. So they're slightly different for train and validation, and both the soft labels are slightly lower means than the hard labels. Okay, now we're getting into training. So at every certain number of steps, we're going to evaluate both what is the accuracy and what are the mean predictions. This can help you diagnose if your model is predicting all 0 or all 1s. And here we're specifying the training arguments. So I would encourage you to check out another tutorial that we're building upon as well, which is about BERT for social scientists. We're using much of the same setup they are. That tutorial goes into a lot more details there, but this tutorial is hopefully one of these meta tutorials that we're showing how we can put these pieces together. So for these training arguments, for your own application, you should do a hyperparameter search for which hyperparameters give you the best metrics on your validation data. Just for the sake of time, I'm just going to choose a single set of these hyperparameters. So for example, our trained batch size and our learning rate and our warm-up steps, these are all fixed. But again, if this is real research, you should do some hyperparameter search here. Okay, so we'll start with this hard prediction. This is kind of what you do with a standard BERT model or any sort of logistic regression model, and we shouldn't need to modify anything. So we're downloading this BERT tweet base and we're using the 4 sequence classification head. This means it's a classification head on top of a linear layer on top of the pooled output. So we specify our trainer with our training arguments and pass in our trained data set and our evaluation data set, in this case, validation, and the way that we want the metrics to be computed. And then we go ahead and train this hard prediction model. And so you can see at first, it's only predicting 1s. The accuracy is pretty poor, but as the number of steps and epochs increases, both the training loss and the validation loss are going down and our accuracy is going up. So that's great. We're still not getting great accuracy on the validation set. It's around 70%. Again, more data and probably better hyperparameter tuning could help here in getting this accuracy up. But for now, we're just going to leave this as what it is. Okay. So now soft prediction. This is when things get a little tricky. So if you uncomment this on your own and try to just use the same exact trainer as we did for the hard prediction, it's going to throw you some errors. And that's because if we pass in soft labels, the standard code doesn't really know what to do with it. But this is one of the big learning goals for this tutorial is we can now modify this code. So if we take the trainer class and we create a custom trainer class that inherits trainer, we can change how internally this Hugging Face model is going to call this compute loss. So we pass in the soft labels, and then during the forward pass, we're going to get the positive probabilities. So probabilities the model is giving for the positive class, and we'll do our custom soft loss function. So we're using, just like we did with the toy data, this binary cross entropy loss, and we're passing in the positive probabilities and these soft labels, right? So instead of this, this hard loss, we're doing this soft loss and propagating this probabilistic assumption throughout. So once again, we load the pre-trained BERT model. We use our custom trainer and the soft labels here to train this. And then we go ahead and train. So similarly, all we've changed here is the loss. We haven't changed any of the hyperparameters or the actual data underneath. So you can see that it's very similar with this soft training. The training loss goes down, the validation loss goes down. It starts with only predicting 1s everywhere, but slowly learns, and accuracy is pretty similar, right? So 0.69 accuracy on the dev set, or validation set, very similar to what we did during hard training. But now we're going to get into, okay, so what did this soft loss and soft training give us that the hard training didn't? And what really matters here is calibration, which we're going to talk about a lot more here in a bit. But that was just a whole lot of information. So let me pause again quickly. Are there any questions in the chat or any questions so far?
Yeah, we have one question related to something earlier. I'll read it out just in case this person doesn't want to read it. Can or how would you compute soft labels when you have a task with more than two classes, so multi-class rather than binary?
Yeah, that totally depends your setup. So if you're doing a one versus rest, which is what a lot of sort of approaches to multi-class is, which means you're treating every single class as a binary classification task of one versus the rest, then you can use the same soft label piece. You're just going to have to redo it for each time you're looking at one class as your positive class compared to everything else. So that's a really nice extension. It's definitely a little bit trickier when you're thinking about trying to do all the multi-class pieces together, but I just recommend one versus rest here. Other questions? Okay, great. So let's take a pause here, and we've gotten into the weeds, but where are we and why does this matter, right? We're doing this classification because we care about this larger pipeline where we're going to aggregate these classifications, and we're going to use this as a variable in our causal effect model, right? So here, even though we got very similar accuracies for this individual trained classifier, what we care about is the aggregation step, and then how that aggregation step gets put into our causal estimates. So one thing that's a little bit different in this setting is that we often care about calibration. So a perfectly calibrated model, by definition, will predict probability estimates that are representative of the true correctness of that likelihood. So for example, if a model predicts a label with 80% confidence, that label should turn out to be true 80% of the time. So we can estimate calibration error by binning these prediction label pairs, and we're gonna use root mean squared error across all of these binnings. And in our pipeline, we would like the above disagreement to be useful for uncertainty. And so we would like our probabilities to be calibrated with the soft labels, right? That's what we're really trying to predict, is all of these annotators giving 0, 1 examples, and then we're going to take the mean across them. So in this little section, we'll eventually end up with these calibration plots where we'll be able to compare these models on how well they're doing. So just a little preview here, and we'll walk through how we get to there. So the first thing is we need a function that can take the predictions and actually spit out a positive probability. So that's what this does here. We check that they're between 0 and 1. And then we're actually going to get the model predictions on the validation data. So we're going to take our trained hard model and our trained soft model. We're going to get the predictions here that are the positive probabilities on this validation data. And we'll just manually check. Again, we can manually check throughout this pipeline that these model predictions are different. So here you can see that the soft model, right, for this first example is predicting a probability of 0.69, but the hard model is predicting a probability of 0.53. So these really are different. Some of them are close together, like this last example, it's about 0.87, but they do differ in the probabilities that are being predicted. And here again, the only thing that was changed between these two models was the loss itself. So we can use standard scikit-learn calibration code to get at what is this calibration error. So we call this calibration curve from scikit-learn. We pass in the predictions from the model, and then also the true hard labels here. We're going to use uniform binning. There's alternatives that you can use, but just for now, we're going to use that. And then we're going to calculate the calibration error as operationalized as root mean squared error. So we have this value. Great, we're going to compare it to the soft model now. Once again, if you uncomment this on your own and run it, you will get an error when you try to pass in the soft labels to the calibration curve. So again, one of the takeaways from this tutorial is if you run into these kind of errors that don't meet your assumption, don't stop, we can modify the code. And so what I did was just go to the place where that error was made. So I'm actually going into the scikit-learn source code, the calibration file, pulling out this calibration curve code, and I'm just going to modify it so that I can pass in soft labels so that this y true doesn't have to be binary. It can also be real valued. So I did that, modified that, threw out that warning, and now we get the same binning that we would with this standard calibration curve. So here we pass in the soft labels from the annotators and the predictions of the from the soft model that's using that soft loss. And we get this soft calibration curve. So we get root mean squared error. And you can see for this soft model, our root mean squared error is lower than it was for the hard model here. So that's good. We're getting better calibration for our soft model with the soft losses. That kind of makes sense here. And if you actually look at this calibration plot, this is what we have. So on the x-axis is the predicted probability from the model. And again, these are binned. And on the y-axis is the fraction or positives, or in this case, it's just taking the mean over the soft labels for each of these bins. And so a perfectly calibrated model would be on the y equals x line. This means if I'm predicting 0.4, 40% of the time, the label is yes, moral outrage. And so what we see here is that our soft model is definitely, so when it predicts 0.4, it's actually, the true number of positives is 0.2. So it's over predicting here. It's giving probabilities that are higher than the true output. So that's something to note, is that even though we got, somewhat decent accuracy of 0.7, we really care about calibration. But if we compare this to the hard model, the blue curve, we're doing overwhelmingly better. And so the hard model is both under predicting and over predicting and is really far off this y equals x line. So this can be really useful in diagnosing which model should you use and why. And in some of these 3.1 plus calibration extensions, there's different approaches to calibration, binning here, which I mentioned, but then also I'll reference this paper, which talks about if we can use calibration to estimate these aggregate values from these classifiers, we can often do a better job. And so we're not going to go into great detail there, but the gist is if you can use calibration error on the validation set to choose which hyperparameters are best, that can help with this aggregate classification problem. So this is just another useful diagnostic to examine how your model is doing and which model you should use. Any other questions in the chat so far, Ian?
Yeah, we've got a good one from Annalisa. You can feel free to ask it yourself, of course, but I'll just read it. Could you interpret a perfectly calibrated model as estimating the intensity of moral outrage in a post?
Yeah, so intensity, right? I would say that, when we think about sort of this aggregation step, which we'll get to at inference time, you really are saying, I want like an aggregate value of someone's overall sort of like body of tweets for a certain time period. And if it was perfectly calibrated, right, if it spit out at that aggregation step 0.8, you would think for that particular user. Maybe your question was about for a particular tweet though. So not at the aggregation step. Does this represent intensity? If you believe that your labels are correct, that, when we looked at that ambiguous 0.5 labeling, that was less intense than an unambiguous, 0.1 labeling, it corresponds to those soft labels. Whether you interpret that as intensity, I think is a little bit tricky. right? For me, I think about it more as like the ambiguity of, is this moral outrage or not? Do people disagree about this or not? And that's not quite the same, I would say, as full agreement means full intensity. Some disagreement represents medium intensity. So I'd be a little bit hesitant to say it's, for an individual tweet, it's purely intensity. If that makes sense, feel free to jump on if I didn't answer your question fully.
I have a more practical question. Oh, okay, thank you. Which is how you choose like the sort of bins, if there's like a procedure for that, or if that's just kind of like depends on the situation.
Yeah, so most people just use kind of a rule of thumb and just choose 10 bins. Here we have a really small validation data set, right? So even though I chose like 10 bins, they only fall into a certain number of bins here because probabilities are only coming out, this is a little over 0.3 to like 0.9. So it's not even spread along the whole 0 to 1 axis. If you have a lot more data that you're estimating this calibration curve and calibration error on, you can up the bin size because hopefully your model is predicting probabilities everywhere along the 0 to 1 line. So like any approximation strategy, right? But the binning is approximating in expectation. What's this calibration error? The closer the smaller the bins are, they're more accurate. But if you have fewer examples in those bins, it's not really helpful.
Yeah, I guess you want some minimum number per bin to ensure like a stable mean.
Yeah.
Yeah. Okay.
Yeah.
Thanks.
And I think so like this paper goes into a lot of different approaches to binning style and some in particular NLP. Both of these papers talk a lot more about like how to both do better calibrated models and also thinking about estimating calibration as well. So I'd refer you to those beyond sort of our very simple example here. Any other questions? Okay, so what have we done? We've taken our annotations, we've adjudicated them. We've then trained a classifier with these two different loss functions, the hard loss versus the soft loss. We've also evaluated calibration and calibration error here. So now we're ready to, at inference time, take our trained model and aggregate the predictions. So unlike Brady et al., who use many Twitter users who are tweeting about Brett Kavanaugh's confirmation hearing, we're just going to use tweets from a public figure, in this case, Alexandria Ocasio-Cortez, just so that we're not impeding on a regular user's privacy. She's a public figure. She posts a lot of public tweets. So I've downloaded via the Twitter API the last 100 tweets AOC made. So for example, she's saying that the very last one, when I scripted this a week ago, when you're showing off the next book, you want banned with the perfect edges and everything to underscore to everyone you haven't actually read it. I think this was a picture of another politician, right? So AOC is somewhat known for the somewhat sassy tweets she makes. And we're gonna encode AOC's tweets with this same BERT tweet tokenizer. And then we're gonna use sort of these data sets that we pass in require the true labels. But here as social scientists, or you all are social scientists, we don't actually have the true labels, right? Truly at inference time, the whole point of taking this trained classifier is that we want to infer tweets that we don't have labels for. So we pass in these sort of bogus labels. These don't mean anything. These won't be used at all. But sort of the paradigm that Hugging Face is using and PyTorch is that you should always be able to evaluate when you're using these tweets. But we're actually doing true real inference here. So this function returns the positive probabilities from one trained model, and we're going to get the predictions from these trained models. So we're going to pass in the text and the hard trainer and the text and the soft trainer. And we run that through our trained models here. And so this is a little function that just takes and prints the actual text and the inferred outrage score from our classifier. And so if we look at for AOC's last 100 tweets, the highest scoring one gets this outrage score of 0.88. And so she's saying, right-wing had a meltdown when I suggested they exhibit obsessive impulses. Tucker Carlson, he's a creep, blah, 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 blah. So if you compare this to the definition of moral outrage previously, a lot of it fits, right? So, you know, if we gave this to annotators, and one way to validate in your own study would be, does it actually match this outrage score? If we gave it to, say, 10 annotators, would 8 out of 10 rate this as moral outrage? That's a way to evaluate, once again, the calibration of your model. If we look at the lowest scoring, outrage score of 0.33, it's just find it here in a link. So probably shouldn't be moral outrage. I would say this probably should be closer to 0.0. Once again, like your actual research project is an iterative process in which you can take these models, you can look at the outputs, you can send them back to annotators, and you can keep iterating until you're satisfied with your model and that it's recovering the social construct in the way that you want it to. Okay, so we've now have inferences on AOC's tweets. And now is the final step of where we're going to take this probabilistic assumption in our pipeline. So we're going to aggregate predictions. The first is hard aggregation. So if we just take the predicted model's hard labels, so binary 0, 1 is this moral outrage. If we just take the mean across these, this is called classify and count in the literature. But we can also do a soft aggregation. So we can take the predicted soft labels, the probability of the positive class. So it's a real value between 0 and 1. And this is called probabilistic classify and count. And so this is a really simple aggregation step, but as you'll see, like there's slight differences in the final results that we get. So we're going to do a sensitivity analysis of these various different models and these aggregation pieces. So if we look at hard model, hard aggregation, we're getting a final proportion, overall proportion of AOC's last 100 tweets moral outrage score. It gives the highest number of 0.73. The soft model hard aggregation is slightly lower, but still higher, 0.71. And if we look at the soft aggregation, it makes both of these scores lower. So the soft model soft aggregation is the lowest on like 0.64, and the hard model is slightly higher in 0.65. Okay, so what, who cares, right? These are kind of similar, right? But if we look at the biggest difference, it's almost a 0.1 difference, right? And so this might not be a huge one here, but it's still big. And if we think about what are we doing, we're taking these values, whatever it is that we get for these values, and then for this particular study, they're using them as the variables in this Y, in this moral outrage piece. So then they're going to put this into a statistical causal model, and they're trying to get the actual causal effect here of social feedback on moral outrage, adjusting for all of these components. So this difference and the sensitivity to this difference could really matter in our final causal estimates. And in other examples, this difference might be even bigger. If there's issues with accuracy or calibration in the models, this difference could actually be bigger too. And so what I hope you take away is that sort of all of these different assumptions we've made throughout the pipeline, they all propagate to this final research question, which is how do we get this value of Y? And both doing a sensitivity analysis and then analyzing things like calibration and the actual tweets you're getting out with their scores along the way can really help you diagnose, do you trust this aggregated classification pipeline that's being applied to your data set in particular. So to wrap up, this whole code base has been all about how do we just get an estimate for this causal variable Y. We haven't really talked about, and we're not going to go into the code of, okay, once you put it into a causal estimate, what happens? but I linked some further readings on people that have been thinking about noisy proxy variables via machine learning or NLP and how they're being used in causal analyses. I encourage you to check those out there. Also, I have another paper where we looked at a different pipeline of economic policy uncertainty, and there these same sensitivity analyses and decisions really changed the final estimate significantly for this particular pipeline. So with that, I'll kind of go back to this major large pipeline diagram, and we have about 10 more minutes for questions.
Well, thanks, Katie. Yeah, as before, feel free to type questions in the chat or just raise your hand to ask them. Oh, we have one right now. Great. Yeah, you can also unmute yourself to ask, but I'll read it right now. So is it a general rule that choices in favor of hard modeling and aggregation techniques will lead to higher values for an outcome measurement, regardless of the underlying phenomenon?
I say no, right? There's it's not that like the hard models and hard decisions are always going to be correct. I think what I emphasized in the beginning, and is sort of my hunch, although there hasn't been empirical evidence about this, is that, right, the more complex your social construct is, and the more this disagreement is a signal, it might be that the soft assumptions are going to help you throughout. But if you have a pretty, we started with that 20 news group example, just is this about science or religion, right? Like that's a pretty hard label, and probably disagreement there wouldn't really give you a lot more signal. Again, this is my intuition and hunch, having done this several times, but it's something that, has not been experimentally, right, like mapping the level of social complexity and then saying, if you propagate throughout, what happens? So I would say what I hope you take away from this code is you have all of these points where you can get metrics like what's the accuracy of these two versus the calibration, versus if I take, and annotate more data and say which ones do I actually believe the predictions for. Hopefully you can make the decisions of which one you want to use in your final research pipeline here. Great question.
I guess I had a basic question, which in this tutorial, we sort of looked at text as the outcome, but do you think this applies to the other direction where you use text as like a treatment variable?
Great question. So there's a couple different papers that have looked at text as treatment. One is Reed Prizan and Danya Schrader's on that paper. She's going to give a tutorial, I think, in a couple weeks in this series. And the other one is from Justin Grimmer, who's at Stanford. And I think Christian Fong is on that paper. Don't quote me on that. I think that's correct. But anyways, people have looked at text as treatment. And the hard thing with text as treatment is you're usually getting one sort of like latent aspect of text that you want to be treatment. And then you have to adjust for the confounding of all the other latent aspects, right? So on top of the issues we have with sort of this aggregation of these NLP classifiers to get a causal variable, in that setting with text as treatment, you have all these additional concerns that you need to adjust for the other aspects of text. That is not quite the same concern as an outcome here necessarily.
I guess I had a high level question too about what your thoughts are on this whole process and sort of like research reproducibility. I imagine that like a lot of studies may not want to sort of enumerate this whole pipeline in their analysis, but I don't know, do you feel like it's important to be able to reproduce studies to have this kind of thing spelled out?
Yeah, so just like any study, I think the number of sensitivity analyses you do really depends on your particular study and setting. You can always do more experiments, right? And have a piece in your appendix where you look at, okay, if we soften these assumptions, how much does my final estimate change? Hopefully it doesn't change very much and your original assumptions were okay. But my concern would be if you don't sort of take some of these soft approaches and you arrive, like you do the sensitivity analysis and your final estimates here are really, really different, right? If this was like 0.3 versus 0.8, right? Like, and there's statistical tests you would probably put on top of this. I'd be really concerned about the validity of your final conclusions. That's what we found in this paper I worked on, is that it really changed sort of what this index was measuring when we made all of these adjustments along the pipeline. So I would hope for your own sort of just like sanity checking, but then also checking for the validity of your own measure, right? Like these are probably things you would want to check if the assumptions fit your actual particular setting. And it's asking for more work, but if we believe we're doing good social science, right, then why would you not check for it? That's my own personal philosophy, though. I'm sure others have different personal philosophies.
Mhm. No, I agree with all that. I think it's, really important to be able to verify this stuff kind of, throughout your poll analysis to ensure that it is valid. Yeah.
Yeah.
Oh, we've got a long one. I don't know if, Indira, do you want to unmute yourself to ask it, or do you want me to just ask it for you? I know I've been talking a lot, so maybe you want to ask.
Sure, yeah, maybe also because it's a bit more general, perhaps. I was wondering, like and first of all, thanks a lot. This was super interesting. I was wondering that in like social sciences, one thing that people do when annotating or like trying to measure complex social constructs, there's this kind of iterative process of coming up with a code book, training annotators. And one thing people often do is like measure inter-annotator reliability. And there are like kind of these rule of thumbs that, hey, if this is less than so and so, that means this is not super good. And maybe this is a problem with the task formulation, that like we need to change, we need to train annotators better, or we need to change the code book a bit better. And so I was wondering, how does that relate to this idea of like disagreement and soft labels that you presented, especially in classification? And more specifically, maybe, do you think that like this type of classification approaches could then be combined with this iteration on the code book, where classifiers could tell us that maybe we need to have another round of designing the code book?
Yeah, I love that. So for your first question about, right, like rule of thumb annotator agreement piece, I'd really recommend, oops, I clicked on it, this survey from Uma et al., which is very recent, about learning from disagreement, both for NLP and for vision. And there they, they talk about how do we move beyond just annotator agreement to things like these soft losses, but then also what you're talking about, which is sort of this joint, like human in the loop, train a classifier, annotate some, figure out, what are, another paradigm is if there's hard items or hard labels, should you just throw out those hard texts, right? Like they're too hard, let's just throw them out, right? That's another thing you can do. And so I would say that, annotator disagreement is a good place to start. There are so many different options and avenues you can go through. And one that they reference a whole bunch of other papers in this survey is that, especially in NLP, we're sort of, some people are moving away from, we should have one true hard gold label. And that, this assumption that disagreement is a useful signal, right? Sometimes that applies. And I'm not saying that applies in every single case, but there is a body of work that's really trying to use this different assumption there. In regards to your second question with iteration, I'm no expert with sort of human in the loop annotation, is what we call it in NLP, but I believe that paper has some references. And then I'll try to think, maybe I can email you offline with some sort of like human in the loop classifier and annotation works, because I can't think of them off my top of my head, but I know they do exist. Yeah, that's a great question.
Yeah, fantastic. That would be super helpful. Thank you.
Mhm.
Cool. Looks like we have one more question from Kirill. Do you want to unmute and ask it, or do you want me to ask it? Up to you.
You can ask.
Okay, yeah, I'll read it. So how would you recommend to handle annotators' uncertainty or disagreement when the annotation task is to label spans inside of text? So like named entity labeling.
Yeah, so kind of like structured prediction span stuff. Yeah, that's a great question. I don't really have a concrete answer because most of what I did with this notebook and my other paper was dealing with binary classification. I would start, again, I'm pointing everybody to the survey, but I do like it. I think they talk about things like NLP tests that are like part of speech tagging and maybe dependency parsing, which are also sort of, you know, either span-based tagging, or I think they do some like named entity recognition as well, in terms of people labeling those tags. But I'm no expert in sort of like the structured prediction space, so I might point you to someone else there. But thinking about extending it, I think it depends on sort of like the way that you set up your structured prediction task too. It's kind of a non-answer, I apologize. Okay, looks like we're almost out of time. Maybe you could post the post survey. If you can take 1 minute and fill out this post survey. Ian and I are always trying to improve this tutorial series and make the next couple sessions that we have even better.
Well, yeah, thanks everyone for coming, and thanks for all your awesome questions. I definitely encourage you to, is it okay if people reach out to you later, Katie, for more questions?
Yeah, please do email me.
Cool. Yeah, we're about time, so maybe we can call it unless anyone has questions. And we'll see you all in 2 weeks for the next tutorial, which, as Katie mentioned, is going to be about